Okay, so in the previous video, we imagined the superposition of two eigenfunctions for the particle in the that's forced to live between 0 and L, and we ended up finding psi modulus squared being equal to a squared. Right? We had some real number a. And so when we square that, we just get a squared. We had sine squared of the first spatial eigenfunction, sine pi x over L. That gets squared. The second one gets squared, 2 pi x over L. And then we had the cross term with the time dependence. Sine 2 pi x over L with the cosine function that involves the energy difference, E2 minus E1 times T, H bar, and that's the probability density. Now we know that if we integrate this quantity over the entire space, then we have to get 1, right? There's a 100% chance of finding the particle between 0 and L. And so what does that translate into for these quantities? Well, it's a squared, and then let's integrate. A squared is just a constant. Let's integrate the quantity that we have there in these parentheses. So this whole thing here goes in here. I'm not going to write it again, right? So it's this whole thing in red. It's in those squiggly parentheses that goes in there, and we integrate that in dx. And so let's notice that we integrate this term in dx, right? That's just 1 because that's something we've already seen before. That's the eigenfunction squared. What's true of all of the eigenfunctions, sine squared of n pi x over L and dx from 0 to L, they all give us 1. So we have 1 for that one, and we have 1 for this, so we have 1 plus 1. And then we saw that, as we expected, the cross term with the time dependence will not contribute to the normalization because it must be true for all times that the probability of finding the particle in the universe in which it lives must be 100%. So that can't be time dependent. And so what we get from this calculation is that a squared times 2 must be equal to 1. And so we conclude that a is equal to 1 over the square root of 2, right? It could be plus or minus. It doesn't make a difference. But the point is that these functions are equally weighted, so we have a solution that looks like psi of x and t. Let's just choose the positive root, 1 over square root of 2. Let's just write them both out. Sine of pi x over L, e to the minus I e1t over h bar, plus 1 over root 2 sine of 2 pi x over L e to the minus I e2 t over h bar. Okay, so that's the wave function. And so we can ask the question, how is this evolving with time? And is there a time when the function, when the wave function becomes one of these two? So is there a time, let's say, is there a t star such that psi of x and t star is equal to right, if the normalization condition continues to be to apply regardless of time, then we could imagine that this evolves to sine pi x over L e to the minus I e1t over h bar, right? Is there a time when psi of x and t is that, or say a time t star, sorry, I put the star as a subscript, let's be consistent, where the function is sine of 2 pi x over L e to the minus I e2t over h bar. In other words, is there a time when the function is now in an eigen state of energy with value of energy E1, or is there a time when the function is in an eigenstate of energy with energy E2, right? There's a fixed value of energy in these two cases, whereas in this it's in a superposition of these two different energies. Is there ever a time when the system evolves in such a way to one of these eigen states, given the psi of x and t, which is a combination of eigenstates, of eigenfunctions? So how do we answer this question? Well, let's maybe try to be as general as possible and recognize that this has something to do with these e to the I terms. So we would need, so let's write out e to the minus I e n t. Let's be more general. What does this look like? Well, it has a real part, right? A cosine of e n t over h bar plus I sine of e n t over h bar. And what we're saying is that for one of these, we would have to get this going to 0. But notice, as we pointed out, that this is the real part, and this is the imaginary part. So they really live in different spaces. So there's no way that we can cancel these two things out. We can't find a value such that this is equal and opposite to that, because there's an I here. And I can't turn this into something times I, so there's no way that I can cancel these things out. So they must be individually 0. Okay, so the cosine and the sine must be 0 at the same time, if it's possible to get this whole thing to be equal to 0. And in this case, we can sort of just look at what we mean by sine and cosine. What are the definitions of sine and cosine? So if here's an angle, right? So in this case, the angle we're dealing with is ENT over h bar, but here's a general angle theta. Here's the hypotenuse. Here's the opposite side. Here's the adjacent side, right? So if the cosine, let's say if the cosine of the angle goes to 0, then what does that imply? Well, that implies that the x side, the adjacent side, has gone to 0, right? So x is going to 0, and then let's see. So how do we make that go to 0? Well, one way to do it is to think of theta increasing to 90 degrees, right? We could also do it negative, but if we think of theta going to 90 degrees, then the x is getting smaller and smaller as our triangle is moving upwards, and eventually we just get a vertical line, and so y becomes h, and so we end up getting that. So x goes to 0, and therefore y becomes h. And so we get that the sine of theta goes to 1, right? If we went to minus 90, then the sine of theta would be negative 1. So that doesn't look like we can do it. Let's think about the sine of theta. So let's say that goes to 0. So what does that mean? Well, it means that y is going to 0, right? The opposite side is going to 0. And therefore it's the x that then ends up becoming h. That's on this side. If I go to 180 degrees, then I get a negative x. But x, and so if I think of it as the angle going to 0 here, x becomes h, and therefore the cosine of theta ends up going to 1. So it's clear that there is no time when psi of x and t is equal to one of the eigenfunctions. So the answer is no. And so we basically conclude that once you have a superposition, it remains, how do you say this, indefinitely as a superposition. So psi of x in t, let's get rid of this, remains indefinitely as a superposition. There's no time when we end up in one of the eigenstates. And so we'll find that when we try to make sense of experiments, we'll say things like the state of the system goes from being in a superposition to being in one of the eigenstates. And it's important to point out that there's nowhere in the solution to the Schrödinger equation, which is this, in this specific case, that allows for that possibility.